Hi, my name is Sajad Muslihi. In this video, I'm going to talk about tracer transport modeling in porous media. Or in other words, I'm going to talk about and I'm going to model the transport of chemical species in porous media. When it comes to tracer transport modeling, we don't consider the presence of chemical reactions in porous media. Maybe no chemical reactions occur actually in porous media, and that's why we're just interested in the transport of the tracer. But sometimes, or most of the times, chemical reactions occur. But maybe those chemical reactions are not important to us, don't affect the parameter that is important to us, and that's why we don't consider them. All right. Tracer transport modeling. I personally use this kind of modeling in order to see the front of the injected water. All right. When I inject water into a porous medium, I have no idea where that water goes by looking at the pressure distribution in the porous medium. But if I inject a tracer into the porous medium with a different concentration, I'll be able to see the front of the injected water, and I'll be able to see, how the injected water moves in the porous medium. All right. It has many other applications. For example, in nuclear waste disposal, or for example, the transport of contaminants. Researchers want to know, and people want to know, how those chemical species, that contaminant or that radioactive, substance actually move and migrate underground. So they do this kind of modeling. All right, that's at least what I know about the applications of tracer transport modeling. Great. So let's get started. By the way, I have created a Telegram channel and also a Telegram group. And if you have any questions related to the videos that I actually put on YouTube, or any questions related to reservoir simulation or petroleum engineering, put your questions on Telegram and ask your questions in that group. All right, and I will put actually the link to the channel and group in the comment section. Very good. So let me get started. So let's talk about how tracer transport is modeled. I have 3 scripts here, which I'm going to talk about. In the first script, I have considered that the concentration of the tracer that I have is in mole per kilogram, which means the mole of the solute or the tracer per 1 kilogram of the solution. All right, so note that this is not molal. Molal is 1 mole per kilogram of the solvent. All right, for example, water. But here I have mole per kilogram of solution. In the next script, I have mole fraction. I'm going to use mole fraction as the concentration. And as the unit changes, the governing equation changes a little bit. Of course, it's not very, big. The change is not very important. But I'm going to talk about both of these units. And in the third script, I'll talk about multi-tracer transport modeling in porous media. All right? Very good. So First of all, what we need to do is to define and discretize the domain, the grid. I've used the function card grid, which is a commonly used function in MRST to create a Cartesian grid in an unstructured way. All right. And as you see, this domain is one-dimensional. It is only discretized in the x direction. And now it's time to see the grid. All right. This is the grid that we have, only discretized in the x direction. 50 cells, the total number of cells. All right. And as you see, the numbers that we see here are different from the numbers here because the unit of length that MRST uses is meter, not foot. All right. So if I put this here, you'll see that this is in meters, 0.3048 meters. All right. Which is equal to 1 foot. Very good. But as you see, the length of the model in x direction is much, much more larger than the other dimensions or directions. But it was not shown here. As you see, it is not very clear that the length of the model is much larger than the other. In the x direction is larger than the other directions. And it's because of the fact that I have not used the function equal here. All right. So let's see the real shape of the model, which is this. All right. Great. All right. In this section, I have specified the rock properties. Let's take a look at the plot, the pore volume of a single cell versus pressure. And as you certainly know, as the pore pressure or the fluid pressure increases, the pore volume increases as well. All right. Let's see what the problem is. Why didn't it? All right. All right. Good. And as you see, as the pressure increases, the pore volume of that single cell increases as well. And the reference pressure is 3,000 psia, which is specified here. And so the reference pressure is this. So the pore volume of a single cell at this reference pressure is 3 cubic feet. All right. And why it's 3 cubic feet? Let's calculate it. The total length of a single cell is 10 feet. Width is 1 foot and height is 1 foot. So the total bulk volume of a single cell is 10 cubic feet. And the porosity is 0.3. So 3 is the pore volume of each cell at the reference pressure. All right. Which is clearly shown here. Very good. Now it's time to define the fluid properties here. I'm not going to talk about all of these again because I have dealt with them in the previous videos. And if these things are new to you, watch the previous videos to get familiar with them. All right. Here I have I'm going to show you the change in the density of the fluid by pressure. And as the pressure increases, evidently, the density increases as well. 3,000 psia, reference pressure, 62, the density at the reference pressure. All right. the density as the reference pressure, which is written here in this function. Very good. Now it's time to specify the boundary conditions. I have an injection well in the leftmost grid block, which is whose index is 1, and I have a production well in the rightmost grid block, whose grid index is NC, which is actually the index of the last grid block of the model. All right, very good. Here I have a specified or calculated the productivity index of the well using the Pisman model, and dz prod is actually the depth of the perforated cell relative to the bottom of the hole or the bottom of the well that we have. Here, the injection flow rate 0.1 stacked iron barrels per day. The bottom hole pressure of the production well is set equal to the reference pressure, and the reference pressure is actually the initial pressure of the reservoir. And the concentration of the tracer in the injected water is set equal to 1 mole per kilogram. And here I have calculated the pressure at the location of the perforated cell, actually by this function here. Actually, this is not a function, but we have calculated based on the bottom hole pressure and the pressure gradient. Actually, the pressure gradient is this, and it is multiplied by this height. Very good. Here I have calculated the initial pressure of the reservoir in this way, and also specified the concentration of the tracer in the porous medium, which is 0.5 mole per kilogram. And as you see, the concentration of the tracer in the injected water is actually higher than the formation water. And so as the water is injected into the porous medium or into the domain or into the reservoir, it's the concentration of the tracer in the formation water increases. All right, it is something that is expected. Here I have calculated the transmissibilities of the interior faces. Here I have actually gotten the discrete differential operators to write the governing equations, and here I have specified the primary variables. The primary variable that we expect to have is pressure, and here, because we have a tracer transport problem, we have the concentration of that tracer as a primary variable as well. All right. But if we have multiple tracers, we have multiple concentrations as actually primary variables, which you'll see here. This is actually the script, which is for multi-tracer transport modeling. And as you see here, we have 3 tracers. In this case, we have 3 tracers. And because of that, we have 3 concentrations as primary variables. All right. And a total number of 4 primary variables. Very good. Very good. The total number of time steps is 50. The total simulation time is 150 days. And that sets a while loop in order to solve the problem for each time step. And here I have another while loop for the Newton-Raphson method. And in this section, in this part of the code, I have defined the pressure equation. And in this section, in this part of the code, I have defined the tracer actually the mass transport equation for the tracer or for that desired chemical species. All right. And for constructing and writing the mass transport equation, which is actually the mass conservation equation of that tracer, we need to have actually the flux of the water. As you see, the flux of the water is used here in the advection term, and here we have the diffusion term. All right. And so the flux term consists of two different terms. The advection term, which is this, and we expect to have this flux term in the flux in the advection term, and the diffusion term, all right, or diffusion dispersion term. And this is actually, this D is actually the diffusivity coefficient, diffusion coefficient, actually. And this is the gradient operator used here. This is the average operator. This is the divergence operator. And I didn't talk about this. This is actually the accumulation term, all right? Or volume of the cell is multiplied by the density of the fluid and multiplied by the concentration. And this will give us the total mole of that tracer in a single cell, all right? In a single cell. And this value is divided by the time, all right, which is required for the accumulation term. In the denominator of the accumulation term, we have time. And in the numerator, we have the mole change, all right, relative to the previous time step. Very good. Or we could say this is the next time step, whose solution is being guessed. And this is actually, the solution to the previous time step, whose solution is already specified. All right, very good. And if we're not interested in this diffusion term, we can use this one. I just removed this term over here in order to only consider the effect of advection. All right, here I have considered only advection, not diffusion. And adding the accumulation term to the flux term. And in this part, I have added the boundary conditions. The transport equation for the injection cell, the transport equation of the injection cell minus the injection flow rate multiplied by the density of the injection water, which is actually the density of water at the reference pressure. It depends on what you're going to, what density you're going to consider for the injection water. And multiplied by the concentration of the tracer in the injected water. And we do the same for the production cell. The transport equation for the production cell or production cells, if we have multiple wells, minus production rate multiplied by the density of the fluid, the density of water in the production cell multiplied by the concentration of that tracer in the production cell. All right, because we did this because we're producing that tracer from the production cell. All right, so we need to use the concentration of that production cell. All right, that's why I used this concentration. But here we have to use the concentration of the tracer in the injected water. All right, very good. And as you see here, we are able to specify the boundary condition for the injection well in two different ways. I talked about this. The other way is this. I can just write the concentration of the injection cell minus the concentration of the tracer in the injected water. Very good. And both of them will give us the same results. And both of them are correct. All right, so very good. That's the whole thing I could talk about in order to model tracer transport. And let me continue running it. All right, great. It was very slow. All right, let's see the result. Let me stop it because the result is already shown in that window. I closed it. So let's see it again. As you see, water is being injected into this cell and produced from this cell. And the concentration of the tracer in the injected water is higher, and so its concentration is increasing in this side of the domain. All right, very good. Because the model is one-dimensional, I was able to visualize the result in this way. But if it was two-dimensional, three-dimensional, this is not a good way to do that. Very good. Very good. And I'm also able to use the MRST GUI module to visualize the results. Let's see. Actually, very good. The pressure distribution, let's play it. 20. As you see, the pressure distribution is no longer changing, and it's because of the fact that the fluid flow has become steady state. All right, the fluid flow regime has become steady state. All right, so at the beginning we had the flow regime of unsteady state. All right, but after a while the flow regime becomes steady state. Wonderful. All right, so and now it's time to talk about actually, yeah, another thing that I'm going to do is to make the model multi-dimensional. All right, it was one-dimensional, so let me make it two-dimensional now. Of course, certainly the computational time will be higher. 100, 100, 100, 100, and very good 100. We just made it two-dimensional. That actually, the domain became larger. So I need to increase the injection flow rate a little bit. 5 stacked ampere per day is good. And now let's run the code. We have an error. The error is that we need to make the well radius smaller because of the reason stated over there. And let's run. And as you see, this time is slow. All right. Of course, the other reason why it's very slow is that the video recorder is running and it makes the laptop slower. All right, so very good. We'll see the results. And now it's time to, let's talk about the second script. In this script, I have considered the concentration of the tracer in mole fraction. All right, there are some changes that need to be made. The input concentration for the tracer is specified in mole fraction here. 0.05 is the mole fraction of the tracer in the injected water, which means that the concentration is 0.05 mole of the tracer in 1 mole of the solution. All right? That's the meaning of this mole fraction. All right. But for actually the let me see the results of the previous run. This is actually the previous script. Let's see the pressure distribution in the reservoir. And this is the pressure distribution. All right, very good. Water is being injected into the first cell and produced from the last cell, and that's expected. And let's also take a look at the concentration. Let me stop it. Let me stop it, and let's see the concentration change. And this is the distribution of the tracer in the reservoir, and after a while, as you see, breakthrough of the tracer occurs. All right. Very good, very beautiful. Let's go to the end. All right. As you see, it is visible that you can see that the tracer breakthrough has occurred. Very good. This is the two-dimensional model. And I was talking about the second formulation. In this formulation, we use mass fraction values for the tracer. In this, as I told you, and I talked about this, for writing the mass transport equations, we need to have actually, mass fractions where we cannot use mole fractions. All right. Let me tell you what the reason is. These are, the pore volume is multiplied by the density. What does it give to us? It gives us the mass of the fluid, the mass of water. Very good. Now, we cannot multiply mole fraction by mass. It won't give us, something good. What we need to get here is either a mole per time, or better to say, actually mole per second, or kilogram per second. In the previous script, what we had here was mole per second, because pore volume multiplied by density is kilogram, and kilogram multiplied by mole per kilogram give us mole, and mole per second is what we have. So this is a mole conservation equation. The mass, the conservation of mole of that tracer. But in this one, we have mass conservation equation. Mole is just another form of mass. So, both of the formulations are correct. But we're not able to use mole fraction here. We have to convert mole fraction to mass fraction. All right, to use it here. Very good. Or here, or here. All of these are mass fractions in the mass transport equations. All right, so I calculated the mass fraction. And for the mass fraction, we need the molecular weight of the tracer. I consider that we have calcium, and calcium molecular weight is this, 40.078 grams per mole, and over the total actually mass. But I have ignored the presence of calcium in the water but you could use it, all right? But I consider that there's no, for the denominator, I consider that there's no actually calcium in it. Very good. It's not gonna create a lot of error, but maybe I'd better use it. For the initial concentration of the tracer in the formation water, we have 0.01, 0.01. Great. And let's talk about the mass transport equations. And here, for each time step, we need to update the values of mass fractions. So I have written these things, which is the same as the one I talked about here. They're the same. And I have used the mass fraction values. All right, very good. That's the only difference. And, X influx is the mass fraction of the tracer in the injected water. And also this one over here, this is the mass fraction of the tracer in the production cell. Very good. And if I run this actually script, it'll give us the same results, all right? Of course, the concentration is that I input were different. 0.05 is the concentration of the tracer in the injected water in terms of mole fraction, and the initial concentration in the formation water is 0.01. And this is the distribution pattern. Very good. Very good. All right. Now, it's time to talk about multi-tracer transport modeling. Here, I'm going to consider that we have multiple tracers. We have multiple tracers in the porous medium. And what I'm going to do here is I have to specify, I consider that we have three tracers: hydrogen, carbonate, calcium. So these are the tracers that we have. I have specified their concentrations in the actually injected water. Of course, I could use any other name instead of these because I have used this unit. Because I have used this unit, I don't even need to use their molecular weights. So, they're just, some names that I was going to refer to them. All right, very good. I could, change them with no difference, to the other, with no change to the other sections of the code. So the influx concentration is the same for all of them. The initial concentration, 3 values for each of them. All right. And here, as I told you, we have 3 primary variables plus pressure. All right. And so we have 3. So we need to have 3 actually mass transport equations as well. All right. And for pressure, the pressure equation. So because the number of the total number of primary variables is 4, we also require to have 4 equations. The first one is the pressure equation, and the other 3 ones are the mass transport equations of the 3 tracers that we have. All right. And I have used the actually, a for loop in order to construct a mass transport equation for each tracer. And because we have 3 tracers, we will have actually 3 here. All right. Prim names actually is the name of them. So we have, 3 times this loop occurs. Very good. Very great. And because we have different chemical species, we could consider different diffusion coefficients in order to see the effect of diffusion coefficient on their concentration as well. All right, very good. let me show you the whole script if you're going to write the code yourself. All right, let me show you the script if there is anything you need to know about this script, and that's it. I'm not going to run it because this is the same as the other ones, and that's it. That's the whole thing I was going to talk about. Let me make sure that nothing is left. Yeah, I talked about everything. And by the way, I'm just going to also remind you about the Telegram channel that I created. Actually, there is a group also attached to the channel, which you can use to put your questions in there. And if I am able to answer your questions, I'll certainly do that. And if you have any questions related to reservoir engineering, petroleum engineering, you can ask your questions there. And I put the link to that channel in the comment section, and you can join the channel through, via that link. Very good. I think that's the whole thing I was going to talk about. And yeah, I hope you found it useful and it helps you learn something. Thank you everybody for following this video, and hope you're having a great time.